minute or two to get this to live stream.
Oh, it looks starting already, no?
The Zoom recording is, then it always takes another moment.
Okay.
Okay, good. I have it both on YouTube and Zoom now. Excellent.
Okay.
So
thank you.
Thank you everyone for joining us again for another week of the Monsoon seminar series. This week we have our lovely speaker, Tomohisa Irino, coming from the Hokkaido University today in Japan. And so before we hand it over to him, again, I just want to do a little bit of housekeeping. So just remember to please type in your questions into the chat that you have for him during his talk. And then at the end of the talk, we will kind of go through the questions through the chat, both here in Zoom as well as through YouTube for those of you attending via YouTube. And then I will ask whether you want to read out your question or I can read it out for you. But otherwise, that's fine. And then if you feel like you would like to ask an anonymous question, you can send it to me independently, or I think there's even an option within the Zoom chat to send anonymous questions. So without any further ado, I will hand it over to you today, and you're going to tell us a little bit about monsoon variability as recorded in the Sea of Japan.
Yeah. Okay. May I start?
Yes, yeah, if you share your screen, please.
All right. And share the screen.
Excellent. Yes, it's popping up. I see it.
Right.
And there's your first slide. Excellent.
Yes, it should be. All right. Okay, thank you, Tara. And and thanks all Peter and Review involving me here. And they gave me a very nice topic, topic for me. And I would today talk about so mainly orbital scale variability of East Asian summer and winter monsoon recorded in the Japan Sea, but using the 7 IODP expedition 346 cores drilled in the Japan Sea. Especially I focus on my question: how to distinguish the summer and winter monsoon recorded in the sediment. So I will use a big sample set to try to answer this small question with the help from the many people I listed here, and Tada-san, Sagan-san, and many participants of this expedition 346 cruise, and recently many help from my students, Arison and Ryuki. Anyway, okay, so start with I'd like to start with the modern oceanography of the Japan Sea now. So the surface circulation is so Japan Sea is semi-closed, enclosed marginal sea, and the surface water is only provided from the southern the strait, Tsushima Strait, as the Tsushima warm current, and this current consists of the East China Sea coastal water, which is so fresher and nutrient rich, and underlain by the relatively saltier and warmer glacial water here. And the East China Sea coastal water is highly affected by the Yangtze discharge. So the change in the Asian summer monsoon so affects the oceanography of the Japan Sea. So this is surface water system. This surface water is water mass interact with the monsoon variability. So probably you don't need a lot of explanation for this. But in the East Asian margin, the summer monsoon is expressed as typically heavy precipitation due to the frontal activity and the autumn typhoon passing to the East Asian margin. Actually, in the progress during the progress of the season, the frontal activity promotes the heavy rain to the northward in the Yangtze River Basin, and so freshwater discharge propagate on the East China Sea, and which influence widely to the marginal sea, and which comes into the Japan Sea like this. Okay, the surface production, so biological production, is maintained by the nutrient supply from the open ocean, and the blooming itself is the early summer or spring to early summer and the late autumn phenomenon. But the East China Sea is only the nutrient supply to the Japan Sea. So basically productivity can be regarded as the summer phenomenon here. And in the case in the winter season, the Eastern marginal sea is cooled down very severely. Okay, so because the Siberian high, and the pressure difference between the Siberian high and the Aleutian low promotes a very strong cold wind, and which cool down the ocean and make the many oceanographic phenomenon in the Japan Sea basin. And so most typical one is probably sea ice formation. And it is so sea ice formation is and occurred in the mainly occurred in the near the Peter's Great Bay in this region, and the northernmost part near the Tartar Strait here. And this is the distribution of the thickness of the ice, and sometimes the super cool water formed here and here, or the brine formed during the sea ice formation subside into the deep Japan Sea Ocean basin, and which penetrates the basin floor. So monitored like this. This winter cooling make the Japan Sea deep water very oxic. And this is the dissolved oxygen concentration profile of the Japan Sea basin. And the red dot is much higher than the open ocean Pacific. Okay, so the modern Japan Sea deep basin is a condition of hyperoxic, and here, and the deep and bottom water. And so ventilation depths is also so recently changes, and it is monitored by the chemical oceanographers. And the dissolved oxygen concentration is decreasing. Okay, in the deeper part of the basin in these 20,000 30 years, and Gamo et al. Interpreted this as the circulation pattern is changing recently in the decadal scale. So namely the ventilation depth is getting shallower and shallower recently. Okay. The Japan Sea itself is the semi-enclosed, and it is separated from the open ocean by the very shallow cell. So maximum 120 meter water depths at the Tsushima Strait and Tsuga Strait, and other straits are very shallow. So the oceanography here is very sensitive to the sea level changes. in the past. And especially during the glacial maximum, and so nearly closed condition make the surface water, Japan Sea surface water very fresh. So very fresh by the fresh water supply from surrounding land, and which makes the very strong stratification above the 500-meter water depth, and which makes the which prohibit the deep convection during the winter time, and finally the very euxinic the bottom water condition was formed during the low sea level periods. And these oceanographic conditions were recorded in the sediments. Looks like this. So probably many people already know how the Japan Sea sediment looks like, and this very typically is characterized by the dark and light layers cycle very frequently, and the top surface sediment is very brown due to the hyperoxic condition recently. Okay, and during the glacial maximum, it contains a very euxinic, dark, and pyrite-rich sediments here, and even in the another period, you see a lot of the dark light, frequent dark light cycles, which is already known to correlate with the dance-card oscillation and so the millennial scale changes. And so dark layer corresponds to the interstadial, and the light layer corresponds to the stadial periods. This dark light cycle is basically controlled by the organic carbon concentration here. So darker the sediment, the TOC is higher. Okay? So as I explained you before, actually the productivity itself is a summer phenomenon. It is the nutrients provided through the East China Sea by the at the Yangtze River discharge, and so organic matter decomposition itself occurs due to the winter ventilation. So this is so I felt that we need to distinguish the effect of summer production and the winter ventilation is necessary to be distinguished from the sediment record to clarify the effect of summer and winter monsoon to the sediments. So classically, it is well accepted the explanation of the dark light cycle in the Japan Sea. So the recent high sea level, the basin as a whole is very hyperoxic, and in the very low sea level, like glacial maximum, the bottom condition is very euxinic. And in between this, the middle sea level periods, the Yangtze discharge or the nutrient supply to the Japan Sea surface make the high productivity and the less ventilated situation during the interstadial, or the low productivity and more ventilated the stadial condition, and this is frequently these conditions are frequently changes in the millennial scale. And basically the oceanic mode change is mainly controlled. We think it's mainly controlled by the summer Yangtze discharge. Okay. So in this interpretation, this summer monsoon effect is more enhanced, emphasized in the explanation. On the other hand, And the winter monsoon itself is directly tried to be reconstructed using the northern sediment cores. Okay, and so Ikehara-san and Itaki-san tried to reconstruct the winter monsoon using the sea ice rafted detritus, counting these black large sand to gravel size particles in the software X-ray photograph, and plotted with the ages. And Itaki also reconstructed the radial area abundance, Cyclado Davidiana, which is proxy of the cold and oxygen-rich bottom water, meaning the probably ventilation. Okay, and so they show a very typical the fluctuation pattern during the last 160,000 years, and they are typically relatively high during the stage 3 and later stage 5. And but the IRD signal or winter cooling signal is not necessarily the same as the radiolarian ventilation signal. Probably the ventilation itself is controlled by the stratification and the balance between the stratification strength of stratification and the convection. So stratification may be controlled by the freshwater supply in summer, and convection strength may be controlled by the winter cooling. So still there's some question about the distinction between the summer and the winter monsoon effect on the sediment composition. And now, so I don't talk a lot about dust today, but so in the East Asian margin, the dust deposition called kosa is typical in spring with very minor contribution in deep winter. And so I think the dust availability is might be so limited by the soil moisture in the source area, and it may be controlled by the summer precipitation. But the dust event frequency itself is probably a function of the atmospheric turbulence or the storm track position, which will be controlled by the winter atmospheric circulation. And so still it is slightly difficult to interpret the meaning of dust flux and compositional changes in the sediments in the East Asian margin. Probably it is clearly some signal of the westerlies variability, and actually so some of the dust reconstruction from the Japanese sediments suggests that the orbital-scale changes in the dust contribution flux looks like this. It's lower in the integration and higher in the glacial times, and lower again in the integration times. But the compositional or grain size or the provenance changes looks like this, and which shows 41K periodicity like this in another case, and it is suggested by this signal suggests the contribution from the Taklimakan or northeastern China provenance, and anyway, so the composition and the amount flux of the dust is changing differently. So one may be controlled by the summer, or one may be controlled by the winter. So dust is also the very complicated mixture of the seasonal the phenomenon. So after the the progress of the late processing understanding of the winter and summer monsoon using the Japanese sediment. And the LDP expedition 346 drilled the seven sites from north to south in order to establish the continuous stratigraphic records with the high resolution physical property, and we aim to make the precise inter-site correlation to control the ages for all the sites. And the sediment cores collected during this cruise covers a very wide range of water depths, theory. And so shallowest 330 meter at U1427 to the northernmost U1422 at the 3,400 meters water depths. So the sediment covers approximately covers the long ages from 1.5 million years for U1427 to even 15 million years for the U1430. U1430, and this is the example of the splice records of the U1424, which is the same as the ODP 790 sites 794, and we drilled at least 3 holes to establish the perfect the continuous splice. So thanks to these frequent dark light cycles, we can fill all the core gaps with the sequence in another hole to make a perfectly continuous splice with the precision of at least precision of millimeter to centimeter with the so correlation accuracy with the centimeter. Okay, because these dark light cycles are 10 centimeter scale frequency. So finally we get the nearly perfectly continuous the sediment records, the splice records like this for all the sites we drilled in the Japan Sea now. And so as I pointed out, these dark light cycles can be correlated basin-wide due to the synchronous change in the productivity or the ventilation events in millennial scale, and so which is so major dark layers are correlated like this, these gray lines, which is consistent with the wide distributed tephra layers. So this correlation was continued down to the 1.5 million years ago. But it is very difficult for you to see if these correlations are correct from such a photograph. So we just plot the dark light pattern using the RGB data. So dark light, and these are all sites from so U1422 to U1420, 6 deeper site. And so probably you can see these numbered layers measure dark layers we correlated among the sites, and even the minor minor dark layers, dark light can be also correlated between the sites. So at this stage, our correlation is only for the major dark layers. So I can talk about the orbital scale changes. But if we establish so finely correlated dark light cycles among all the sites, we'll be able to discuss the millennial scale synchronous changes happening in the Japan Sea basin. So this correlation is continued to the 1 million years ago and down to the 1.5 million years ago. Below this, the correlation is not very easy due to the unclear the color or unclear change in the dark light cycles. Okay, as for the age model for the Japan Sea sediments, we established one the precise one at the U4024, which is very typical sequence in this core set, and it is very well. It has been known that the Japan Sea sediment is very highly sensitive to the sea level changes. During the high sea level, the enhanced the eastern sea coastal water inflow was enhanced, and which promoted the high diatom productivity. So which means that the sediment contains a lot of diatom fluctuates during the high sea level period. So which makes the sediment porosity very high, and the bulk density of the sediment would be very light. So this is the GRA bulk density profile. Okay, light, heavy, light, heavy, light, heavy. Okay, pattern of the U1424, and which can be correlated well with the sea level proxy like the LR04. Okay, and so heavy it's the heaviest part, and this maximum of the bulk density is correlated with the glacial maximum, which is associated with the thick the euxinic dark layers. Okay, and so now we have the nearly orbitally tuned edge model for one site, and which can be projected to the other side using the these dark light cycle correlation. Okay. As for the U1427, which doesn't have a very clear dark light cycle, the Sangawa et al. 2018 they established the finely tuned edge model down to the 1.07 MA, utilizing the basic foraminifera oxygen stope with the subtropical radiolarian fauna as a integration proxy, and some the wide distribution in tephras, okay, to correlate with. And it is very well constrained with the open ocean Eastern Sea benthic derivative records, and which established nearly same precision edge model as the other Japan Sea cores. Okay, now we can utilize the nearly common edge models for the 7 segment cores in the Japan's IODP cores. So I'd like to utilize them to reconstruct the spatial temporal variability of total organic carbon flux for the last 1 million years. Okay, and because all the they are all IODP sites, so they all has the RGB data or RGB and dry bulk density or bulk density data, and we have the relatively precise common age model, and the sediment darkness is very well correlated with the total organic carbon concentration in the sediment. So we can relatively easily calculate the TOC flux. Okay, on the TOC barrier flux at the sediment in this sea is probably controlled both by the productivity in summer and ventilation in winter. So I will try to distinguish these effects from these sediment data set. Okay, so TOC was estimated from the photo RGB, and simply speaking, the darker the sediment, the higher the TOC concentration. It is not linear, so the review Jusan gave me the most appropriate calculation equation like this, and I calculated the TOC using the RGB data, which was taken every 5 millimeters throughout the sediment column. And the linear sedimentation rate is already calculated for each site using the U1420 age model established in the U1424, okay, tuned to the LR04, okay. And the bulk density is calculated using the GRA data, which is equivalent to the wet bulk density, assuming the same grain density, so average grain density for each site. Okay, so just multiplying the sedimentation rate and bulk density and TOC organic carbon percent, we can get the mass temporal variability of the mass accumulation rate of the organic carbon for all the sites. Okay, and this calculation is done on the each 1,000 year step. So this is a result. They're very simple. Okay, the data is from shallow to deep. Okay, this is calculated the organic carbon, total organic carbon mass accumulation rate. Okay, and this is LR04 glacial integration cycles, and just take the average and the standard deviation of each data of each depth, and you see the exponential decay of the organic carbon mass accumulation rate from shallow to deep, and I mean it's very reasonable, and so pattern of fluctuation is similar for the deeper site, but slightly different from shallow sites to deeper site and middle the middle depths, intermediate depths. Okay, so I try to distinguish what kind of fluctuation pattern was hidden in these 7 profiles, temporal profiles of mass accumulation, right? And so just conducted the principal component analysis for these 7 data set, okay? And this is the result, okay? So the 7 sets of 7 TOC mass accumulation rate data sets are summarized into the so explained by the combination of these 3 major fluctuation pattern of TOC flux. Okay, so these 3 can explain the approximately more than 70% of the total variance, and I'd like to look at the each pattern and the meaning here. So score is plotted like this. So they are all different, and they are loading. So in this case, the principal component loading is how the each site. So each site in various steps contribute to this variability. Okay, in the case of principal component 1, and all the sites, all the depths varies at the same time like this. Okay, so positive score means that the increase of the TOC flux for most of all the depths. Okay, and in the case of PC2, so positive score mean the higher, relatively higher TOC flux in the shallower part and relatively lower organic carbon flux in the deeper part. Okay. In the case of PC3, if principal component, third component, principal component is positive, only the intermediate depth organic carbon flux is depleted, and the deeper part is enriched. Okay, relatively. Okay, so the interpretation of my interpretation to these so loadings. Okay, now principal component loadings, and so in the case of PC1, so all the water column responds at the same time. Okay, positively, or if negatively. Okay, this is just the whole water column enrichment or depletion of the organic carbon deposition. Okay, which suggests the change in the export production. Okay, so very easy. If I plot it to the average the water column TOC flux, and positive principal component loading means the profile changes to this red line, and negative principal component 1 means the change the TOC flux profile like disproven. Okay. And in the case of PC2, it is only the deeper part TOC flux is so reduced. Okay, or shallow part is relatively enhanced, and which means that the so average the TOC flux depth distribution is changing like red one if the PC2 score is positive, and in the case of PC2 score negative, the profile changes like this, which suggests the ventilation depth was deepened. Okay, if the PC2 score is positive. Okay, so deeper ventilation reduced the TOC flux at the deeper part of the basin. The PC3 is certainly interesting. In the case of PC3 score positive, the intermediate depth TOC flux is relatively depleted. Okay, and the opposite for the deeper part, which means that the when PC3 score is positive, so mid-depth ventilation was enhanced, and in the negative case, it is opposite. So it is so very difficult to interpret them, and I try to find the similar similar signal from the previous data or the data recently my student made. And the first, so PC2 score shows such fluctuation pattern, and we, or so Mr. Saijo, my student, made a data this year, and this is the detector sand content in the U1422 northernmost site, and which is interpreted as the sea ice rafted detritus amount contained in the sediments. And this is typically the low recently in Holocene and high in glacial times, low in the interglacial times. And so it is clear to see the orbital scale changes. And when I compared it with the PC1, PC2, PC3 profiles, the PC2 score is very similar to this, oppositely, negatively correlated. I mean, when the IRD content is high in the northern side, and the PC2 score tends to be negative. Okay. So like this. So especially this part, the opposite pattern is very, very clear. Okay. So which says that in the case of PC2 score, the positive value indicate the deeper ventilation, and the negative value is opposite, so shallower ventilation. And in the case of IRD, usually it is interpreted as the CS expansion. If it's higher, it suggests the CS expansion, and if it's lower, CS shrinkage. Okay, this fact suggests that the CS expansion may inhibit the deep convection, probably due to the surface water is covered with ice, sea ice, during the winter. Okay, it is our interpretation. And as for the PC3, okay, it is an intermediate depth ventilation enhancement. It is very in the top 160,000 year part is very similar to the radial radian ventilation indicator I showed you before. And so the low negative PC score is associated with ventilation. So high ventilation radial radian proxy, okay, like this. Okay, so there's inconsistency due to the inconsistency of the edge model. This part is not very clear, but probably the basic feature is very well reconstructed also by the PC3 principal component 3 and the profile. And in this case, the positive PC3 score means the intermediate depth ventilation, and the negative means the deeper part ventilation. And this is just the radial area suggests so active ventilation or inactive ventilation. So these two signals so looks very consistent. Okay, so this is okay. This is I stop here for my the consideration at this stage. And so anyway, so I reconstructed the spatial temporal variability in the Japan Sea basin, variability of the total ionic carbon in the Japan Sea basin for the last 1 million years. And the reconstruction itself looks reasonable, and the fluctuation patterns are classified into 3 principal components. So principal component 1 suggests the export production, which may be was probably controlled by the summer monsoon effect or sea level. And the PC2 is suggests the deepening of ventilation, and the PC3 is more enhanced intermediate depth ventilation. And the comparison between the PC2 and the sea ice rafted detritus suggests the sea ice expansion may have inhibited the deep convection at that time. And so I like to summarize summarize what I learned here is that East Asian winter monsoon may be expressed in the here is sea expansion. So it's expressed as the CX expansion and strength and or depth of convection here. So it is slightly complicated. So further fine-tuning of dark light correlation will enable us to discuss the millennial scale variability of this region with the monsoon using the similar method. Thank you for listening. Okay. Okay.
Great. Excellent. So I guess we'll allow people a minute or two to type in some questions within the chat, and then we can get to those. But the recovery of the IODP course in the Sea of Japan looks like it's pretty good. And then they're absolutely beautiful cores with the light and dark variations. I had not appreciated that, to be honest, and that is really quite cool what you can do with the light and dark variation. So
it's just beginning. We just finished the and the stratigraphy.
There's still so much to do, which is great, right?
Yeah.
Let's see what's in the chat. Let people get to the questions. You already covered one of my questions, which was I was going to ask you about loess in the Japan Sea, because I know that the news, of course, had been talking about, this big dust storm, of course, that moved through China and probably over into Japan just, I think, a couple weeks ago. But you covered that.
Probably Shimin will talk about the dust a lot later in this series.
And
Yobin also.
Yeah. And so just to double check again, so your cores go back about 1.5 million years?
1.5?
1.5 million? Is that how far back?
Yeah, typical dark light cycles can be traced down to 1.5, probably 1.45 or so.
Okay. Wow.
Below that, the appearance is very different. The atom-rich, rhetoric, so homogeneous appearance.
So I noticed at the very top of your core that it was, of course, and you mentioned this, it was quite red, but there weren't, at least in the appearances of some of your slides, they weren't nearly as red deeper in the core. Do you think that's a preservation issue, or if it's more of an actual difference in signal?
No, probably brown color is the manganese and iron oxides, so it migrates upward or always. Okay. Due to the aridagenesis, so it's not kept.
That's okay.
Probably, but modern sediment will be light layer. Several thousand years later.
It's just my land ignorance. That's all. Excellent. Well, does anybody else have any other questions here that are burning to ask? But I think everybody's been duly impressed by the amount of work done on the course and are kind of looking forward to what's coming next. Okay, well, I have actually one more quick question before I will let you go. So in terms of the sea ice expansion, you mentioned that it's controlled mostly by the winter monsoon. Do you think that maybe some of the sea ice expansion is probably more of a global signal rather than more of a monsoon signal? Because it did appear to be looking like it was controlled by more of these interglacial glacial cycles, or I don't know if you can tell that yet, just based on some of the prior talks that we've had in the last probably month or two.
The millennial scale behavior suggests it is probably at least the hemispheric phenomenon related to could be related to the Dansk-Adolfsco polar circulation changes in millennial scale. But in the orbital time scales, it is just look like the glacial interglacial changes.
Okay. All right, thank you. All right, well, I'll give somebody a last chance here to ask a quick question. Otherwise, we can let you go for the evening and you can relax for the rest of the week.
Yeah.
All right, we'll put together a virtual applause for you. And again, thank you so much for telling us about some of your excellent work and those of your colleagues, of course, and your students. So before everybody runs away, I just want to make sure everybody knows that next week for Schedule A on the 21st of April, we have Pallavi Anand giving a talk. And then the next speaker for Schedule B on the 28th of April will be Jifei. So please come back next week and the week after, and we'll discuss a little bit more about Monsoon. So with that, I guess good morning, good afternoon, and good evening for the rest of you. And thank you very much again, Toma, for your excellent talk. Okay.
All right.